going on, YouTube? My name's Jordan. I'm a mechanical engineer, private pilot, and I love 3D printing. Today, I'm going to be watching and reacting to mechanical engineering Slander. I am a mechanical engineer myself, so curious to see what kind of jokes, inside jokes are in here, and I will do my best to explain them to you so you can get them as well. So, went to school for mechanical engineering, like I said. I'm 3 years out, 2.5 years, 3 years, whatever. Close enough. I've interned at a couple of different places, and I've been full-time at a company in my current job for basically 2.5 years. Interned there beforehand, so love what I do. Gotten to do a lot of cool stuff, meet a lot of cool people, and I've learned quite a bit so far in just my 3 years being out. So let's get right into it. See what's going on here. Okay, yes, Excel. So I have a story for this. So knowing the only important career skill is Microsoft Excel. Yes, 100% agree. 100%. Well, other than Word, but to make your reports. But Microsoft Excel, I've never used it more than my one professor's class for heat transfer. That's the most I've ever used Excel in my life, and I've become I would say a pretty high level black belt because of it. And I will show you exactly what I mean. So this was when COVID just started in like March, and at least in America, everything hit the fan in March, basically. I went to spring break and didn't come back. Stayed in basically my parents' basement because I moved back home from college. And I didn't have COVID, but I had like this pneumonia. So I was sick anyway, and they're like shelter in place and everything for 2 weeks. Well, I didn't literally come out of my room for like a month. It's pretty bad. But anyhow, I spent a lot of time just doing class, obviously, and everything was more difficult. And so this Excel sheet is no joke, 8 hours solid of work for heat transfer. So basically we're solving, I forget what we're even solving for. This was like 3 years ago. So, but you have all your temperature ends, this is for heat exchangers. So you have concentric tube heat exchangers, you have shell and tube, the plate heat exchanger, and then looks like some discussion here. But you input your counterflow, your parallel flow. So that's where you have a cold flow from this side going this way. So counterflow would be the hot flow coming in this side. Parallel flow would be both flows, obviously, coming in from this side. And I'm still full cam, so sorry about that. But you didn't miss much from the video anyhow. And then, so you have varying temperature, varying flow rate. You can do all kinds of stuff with that. So yeah, here we have a constant flow in liters per minute, it looks like. And then we have the flow varying. Looks like for the cold, the hot is constant, the cold is varying, and you get certain amounts of heat transfer. Here's your specific heats. And some of them change as well. You have interpolation for looks like your mass flow rate times your something or another, times your specific heat. There's a lot going on here. I don't really remember what's going on, to be honest, but it was a lot of work, and this is just one of the many Excel sheets. So you most likely, if you're mechanical, will become a master at Excel, either in college or in the workplace. Yes, literally had this happening when I was in California. I've been all over the country in November, so that's why I haven't been putting out videos. I was literally in St. Clemente Island, which is, can't spell, don't care, in the middle of the ocean off of San Diego. So San Diego's right here. Traveled all the way up here, was on San Clemente for a test, and then the wife and I went to New York for Thanksgiving. So I've been all over the place in November, so that's why I haven't been putting out videos. But to that point, I was actually in San Clemente. We have Starlink because there's like nothing there. There's some cell service if you have the right carriers, but I was on Starlink into our VPN doing SolidWorks, and it was just so much latency involved, and it crashed literally 4 times within about 3 or 4 hours. Very, very frustrating. Save often. I don't really get that one. Most replica car after more than a century of R&D. I don't really get that one. Okay. So this is hearing sum of the forces is equal to 0. So that's, you'll hear that over and over in statics. So when you have a statics problem, so you have a force vector in this direction, you sum the forces in the x and you sum the forces in the y, and you do trigonometry, sine, cosine, tangent, and then you can get resultant forces in each component, and sum of forces in x and sum of forces in y. So you'll hear that, and it'll probably show up in your sleep too. You'll be dreaming of sum of forces equal to 0. Yeah, that's kind of true. Of course, I use hand calculations and experimental results. Yeah, that kind of some people do that. A lot of the time, we're just, it's FEA. I don't have to do the hand calculations. It's fine. But when you do, and they both agree, very satisfying. Especially for heat transfer, you do the resistive method. That's pretty cool when you do that. Yes, this literally at my job, literally McMaster-Carr, they have CAD models, standard, screws, nuts, bolts, whatever, and then you can order it. It's like Amazon Prime for engineers. It's legit. Literally used it today for several things. That and 8020.net. So 8020 is like the T-slot aluminum. I'm sure other places have CAD models of stuff, but 8020 has some really nice CAD models, and I just literally made a cage with some other stuff today, so. Oh, that's some nice laminar flow. So if you don't know what laminar flow is I could be super technical about it. Laminar flow Reynolds number, let's see. I forget it off the top of my head. I know it's 5,000 something. Flow Reynolds number. Okay, maybe not. Larger than, so all Reynolds number basically describes is the how turbulent your water is. When you're laminar like this, everything's really nice and smooth. When it's turbulent, it's going to be broke up, and so laminar flow is just really satisfying. But what you don't want laminar flow for is telemarketers calling me. What you don't want laminar flow for is heat exchangers, actually, because you get a boundary condition. Let's see, laminar flow boundary layer. Yep, boundary layer. Let's see if there's a good picture of this. Yeah, here's a good picture describing it. So basically you'll get, that didn't really pan out well, but you get this swoop effect here. If you would imagine a line in front of it, I can just draw it real quick. Let's do that. And where'd you go? There you go. Okay. Now we can draw. Let's do red. So you get this gradient. So basically what's happening here is you know how your physics professor or teacher in school always said, well, technically if you're touching your fingers together, you're not really touching. There's like atoms, whatever, this boundary. It was like, huh? But there really is, especially in when you're looking at fluid flow, there is a boundary layer where, super, super close to this surface. Let's say this is the inside wall of a pipe where the water is not moving. And so when you have laminar, that's especially true because it's nice and smooth. So think of this as your heat transfer percentage. This being 100% transfer, even though that's not necessarily true. And down here is like 20% transfer. So it's only transferring 20% of the energy the heat, let's say, in that pipe. Whereas when it's turbulent, you have a higher percentage, say it's like 40 now, that it's turbulent and it's breaking up that boundary layer down there. So that's why that's important in heat exchangers, which are in really at least my computer, I have an AIO, which is a all-in-one cooler radiator system. Some other people might have that, but that's important in your car. So pretty cool. Everything at your job that isn't a spreadsheet. Oh, it's blank, so everything is spreadsheet. I get it. Yeah, that's right. That's mostly true. So I literally have so I was an intern, and then I've been asked to kind of help mentor the interns over the past couple of years, and I literally have a drawing I've kept, and I literally wrote in big Sharpie letters, "Do not do this." It is the biggest abomination of a drawing I've ever seen. There's dimensions on the drawing. There's literally, you can barely see it's a sheet metal piece with one bend in it and a bunch of holes for fans and stuff, supposed to go in a Pelican case. It is the worst drawing I've ever seen in my life, and I purposefully kept it, and I have it in a folder in my desk. I've kept it for 3 years so far for incoming interns, and I literally whip it out and I say, "Please, for the love of God, do not do this. Ask me if you have any questions, or somebody else. Do not do this." And it's so true. Most people are pretty okay at it, but this guy in particular was a 5-year master's program guy, and he made sure you knew about it too. So a free body diagram is kind of the ground. It's the first thing we were always, and my professor was super intent on doing this, which I'm glad he did force us to do it, is he gave us points for just drawing the free body diagram. So that's basically kind of our incentive on the test to be like, well, and it's really the foundation of the problem. If you can't draw the free body diagram and properly model it and dumb down what's happening, then you're gonna have a really hard time with the problem. So free body diagram, basically that guy in the chair, you could combine as a dot and then draw X and Y, and then you sum forces in X and Y, so on and so forth. So if you don't draw a free body diagram, you're just kind of like not grounded, if that makes sense. It just goes back to how you kind of work through the problem. It's a good foundation. I'm trying to think of a good analogy to do. It's like, it'd be like trying to run a marathon with slides or sandals. It's just you're not wearing the right footwear. You're not doing the right thing to get started. That's maybe not the best analogy, but that's all I got at the moment. Yeah, this was always fun doing, not fun being not converting your metric to imperial units. However, I will say, I love America, but metric units are much easier to do lots of calculations with. But at the end of the day, it's harder for me to relate to it. It's not as tangible, I guess, as what I'm used to with miles per hour, feet per second, feet, yards. I know meters, basically yard more or less, but meters per second and kilometers and kilograms. It's like, I know the rough conversions in my head, but it's more tangible if I use, imperial units. But they are a pain to work with conversions, because you have to multiply them like pound mass. You have to multiply stuff by gravity, and then kilojoules to watts, and then, what's the imperial for that? What was that? I think that's it. Yeah, kilojoules to watts, because you got a joule second is a watt, and no, that's a straight conversion. I don't know. There's other ones that are just, they just haunt me. I guess you have to, and then you forget them on a test, and then you lose points, and it's like, oh my gosh, forgot about that. So You're like, huh? Mass and weight, they're the same thing. Yes, they're not. So mass and weight is weight mass times gravity, because you can have mass on the moon that does not weigh the same as it would on Earth. You can have 5 kilograms of mass, or whatever your mass unit is, 5 units of mass on the moon, and it weighs 2 units of weight on the moon, and you can have 5 units of mass, it weighs 5 units of mass on the Earth. Whatever, that's not the exact conversion, but you can see the difference there. Mass is by itself, weight is mass times gravity, or whatever your acceleration force is. So that's a fundamental. So this is like the same beef as you see on like TikTok with mechanics looking at cars and their designs and being like, this is the dumbest design in the face of the planet, which some are, I agree. But especially with young engineers, me being one of them, I've made these mistakes before. But I had a lot of good internships and mentors over the years that I've been interning and learning things that have really helped me not make a lot of the same mistakes. But young engineers are, they'll dimension stuff wrong or with impossible tolerances or tolerances that kind of just grind machinist gears. Like, it doesn't really matter. Like, do you really need it? Do you really need a fillet that is in a size that is not the end of, the diameter of an end mill, like a ball end mill of, so like a ball end mill with a fillet on it that's a 1/16 of an inch would leave basically a 16th inch radius. But if you wanted some radius that was in between that and another bit size, it's like an impossible radius, and it's just like, really? So that goes back to making your parts cheaper, because you're not going to drive people crazy with trying to get super precise, non-common radii. It would be, I guess, something to the equivalent of you requesting a shoe size for, like, shoe sizes go in like halves, at least in America. So 10.5, 11. It'd be like you trying to get a 10.2 size shoe, which like doesn't exist. So it'd be like the same thing. So it's always the same struggle, especially welders too, because you get into welding parts, and literally if you weld a piece of a metal straight like a T and you down one side, when it cools, you'll literally see it bend like a good amount depending how long the piece is. I've done quite a bit of welding, actually. My one internship, I basically welded every day, made fixtures for a laser robot, and made some other cool designs and stuff like that. But the opportunity to do a lot of welding, aluminum on welding as well. So so there's always this beef, much like mechanics in the engineers, but machinists and welders, it's basically the same thing. What's that? You guys with 30 years of experience using 100% of the brain to over-design a simple Okay. Yep, that's true. So one thing that I've gotten into the trap of over-designing and making things super fancy and elaborate, and it's like, but it doesn't need to be. So keep it simple, stupid. I always try to go back to that and bring myself back down to earth with that. You don't need to reinvent the wheel. Just make it simple, get it done. You're usually graded on if the job gets done, not how really it gets done. You could spend a ton of time and more effort into something, and the other guy next to you could get it done and accomplished within the requirements, and it could be less complex and less costly. So just have to assess the situation and go from there. I'm not far off. I took it in the defense industry, so not too far off. But I do kind of want to get into aerospace someday. That would be kind of a dream of mine because I am a pilot. I like that kind of stuff, especially rockets. That'd be really cool. But it makes sense. We, as mechanicals, do a lot of analysis with forces. So you have, honestly, lots of forces, fatigue, design. Mechanical engineers are primarily design engineers. So they design and test stuff, and that's how planes get built. That's how rockets get built, et cetera, et cetera. So looks like we're almost done here, and that's it. All right, well, that's reacting to mechanical engineering Slander specifically, part 1. Probably do a part 2 of this, and it'll be up shortly thereafter. So let me know if you enjoyed this. Drop a like, drop a sub, excuse me, and let me know what I should react to next. Thanks, guys. Peace.